So this was T1 was mg, T3 was mg, T2. T1 was mg, T3 was mg, and T2 was 1.41 mg. So those were the tensions in the cable. So let me ask you this. All right, so you wanted this sign to hang there. Why not just hang with a single cable? And this cable, it would have to do is mg. Instead, you put this structure. This was mg, that's fine. But this was 40% greater, so you had to buy a more expensive cable. Why did you do this? What? Yeah, so this was more stable. That's why you did that. Okay? So that's the reason why you do various things. Okay? So you were willing to spend this extra money. Okay. A small 1,000 kg SUV has a wheelbase of 3 meters. If 60% of its weight rests on the front wheel, how far behind the front wheel is the wagon's center of mass? Okay. So the wheelbase, this is 3 meters. So the weight of this guy, mg, okay, this force is 60%, 0.6 mg. And so this force is 0.4 mg. Okay. They're asking you, so this is center of gravity, they're asking you x. Okay. All right, so what we'll do is, so this is in static equilibrium, and these two conditions must be true. And generally, all we'll have to do is use one equation. Okay, so mg and 0.6 mg and 0.4 mg are being balanced. That's trivial. Okay, so here's mg in the downward direction and 0.6 and 0.4 mg in the upward direction. So to calculate x, what we'll do is let's calculate the torques of these two forces about the center of gravity. So this force is trying to rotate the car counterclockwise, and this force is trying to rotate the car clockwise about that point. Okay. All right, so counterclockwise torques are positive and clockwise torques are negative. And this distance would be 3 meters minus x. Okay. So minus 0.4 mg times 3 minus x plus 0.6 mg times x equal to 0. So mg cancels. Minus 1.2 minus 0.4 x plus 0.6 x equal to 0. So 0.2 x equal to 1.2. What happened? I'm sorry? Mm-hmm. Okay, so x equal to 1.2 meters. All right, so if this was 50-50, then x would be 1.5 meters. Since the load here is greater, that's because the engine is in the front and the center of gravity is closer to the front wheel. Yep. All right, a uniform plank rests on a level surface as shown. The plank has a mass of 30 kg and is 6 meters long. How much mass can be placed at its right end before it tips? Okay, so they're asking you how much mass can you put there. Okay, so this mass is trying to tip it over clockwise about this point. We'll calculate the torques about this point. And there's the center of gravity. That's the weight, that's where the weight of the plank is acting. So this weight is trying to tip it over clockwise like this. This is the counterbalancing torque holding it back. Okay. What is this distance going to be? So the thing is 6 meters, so that is 3 meters, so this would be 1.2 meters. Okay. All right, so we are doing sum of the torques equal to 0. So, and M is 30 kgs, but anyway, little mg, this is a clockwise torque, so it'll be negative minus little mg times 1.8 meters plus mg times 1.2 meters equal to 0. So m equal to 1.2 divided by 1.8 m. Okay, so okay, so you're further out, and so the maximum mass is 2/3 the weight of the plank. Okay, so the heavier the weight you want to support, the greater should be the plank weight. Okay, the heavier the plank, the greater weight you can support. All right, so here's a little more involved problem. Okay. So the uniform boom shown below, when they say uniform boom, what does that mean? That's right. So that's what they're trying to tell you. Okay, their center of gravity is at the geometric center. Okay, weighs 700 newtons, and the object hanging from its right end weighs 400 newtons. The boom is supported by a light cable and by a hinge at the wall. Calculate the tension in the cable and the force on the hinge on the boom. Does the force, okay, so what we want to do is we want to calculate this tension, and by the way, so this is 700. And they don't give the length of the boom, so we'll call it L, okay? And the reaction force. All right, so what we'll do is we'll calculate, for the first part, we'll calculate the torques about this point, so this force will not come into play, and we can calculate the tension, okay? And then what we'll do is we'll break down the tension into this component and this component. Okay, so this is T sine 45, and this is T cosine 45. All right, so for the first part, for the tension, okay, let's calculate the torques about this point. Okay, so this force, the moment arm is this distance, and that distance is L by 2 cosine 20. That's a clockwise torque. So minus 700 Newton times L by 2 cosine 20. And then the moment arm for this guy is L cosine 20. Okay, so minus 400 L cosine 20. So that's a clockwise torque. This is a counterclockwise torque. This is trying to rotate it counterclockwise. This is also a counterclockwise torque. The moment arm for this guy is that distance. The moment arm for this guy is this distance. Okay, so T sine 45, that's a counterclockwise torque, L cosine 20. For this guy, that is the moment arm, which is L cosine 20. For this guy, this is the moment arm, which is L sine 20. And they should add up to 0. Okay? Did you guys understand that? All right, so let me, yeah, go ahead.
The L, what did you get L over
Okay, so the weight of this guy is acting in the center. This is L over 2. The whole, yeah, yeah, that was L, length of the boom. This is L over 2, and this is the moment arm. And so L over 2 cosine 20.
So the cosine 20 is the x component of the distance.
Well, yeah, so the perpendicular distance, this is vertically down, so this distance is, so this is the right angle triangle. Okay. Again, this force is rotating the boom clockwise, this force is rotating the boom clockwise, this force is rotating the boom counterclockwise, this force is rotating the boom counterclockwise. Okay. So you see in this thing, L canceled. That's why they didn't give you L. Okay. And T is the only unknown, so you can calculate T. Okay, so let's do this. So the first term is minus 328.9. The second term is so you see the tension in the cable is, so actually that's pretty good. So you're supporting 1100 newtons with 783 Newton tension. That's the tension in the cable. All right, now we want to find this guy. So again, what we'll do is we'll break it into x and y components. So okay. So the x components, this force has this x component, this x component, and this is the only other force that has an x component. So this should be balanced by that. So Rx is equal to T cosine 45. So the x component of the force, Rx minus T cosine 45 equal to 0. Yeah. Again, you guys see that this force is balanced by that force. So Rx is and then for the y component, this y component plus this y component is balancing these two forces. Yeah. Ry plus T sine 45 minus 700 minus 400 equal to 0. And T was okay, so R is the x component is 553.7 I plus 546.3 J. And if you calculate the angle the R vector makes, that's tan inverse of Ry over Rx, 546.3 over 553.7. So this force is at 45 degrees and the boom is at 20 degrees. So the reaction force is in that direction. Okay. All right, guys. So we will